today's subjects. I'll just get my PowerPoint up, so it should be full on that.
From burners.
Some stuff yesterday.
Yes.
There we go. Okay, doke. Okay. Ready to rock and roll again. Right. So hopefully, I say fingers crossed, we'll get the new books out hopefully by the end of the week, because I'm sure it'll take a little while to print all the new books out for you. But just make best of the old books at the moment. It's not far off books 1 and 2, but again, it's been moved about, as I say. And the new books have revision questions in them as well, which will help you for your revision to keep up to date as well. So, what was that? Okay, Sanjeev just replying. Good. Right, okay, well, go forward. Oh, what's happened there? The joys of technology. Right, let's just check that. Bear with me 2 seconds. Okay. Right, eventually. Right, okay, so we've done sort of the cold part yesterday, compressors and airflow control and that sort of thing. So I'm now going to move on to sort of the hotter part, where we put the fuel in, combustion chambers, etc. Okay, and we'll look at the different types and bits and pieces that goes on within there. So I'm going to start off with burners. Now the burners are the components where the fuel flows through into combustion chamber, and depending on the type of burner, we'll distribute the fuel either by vaporizing or atomizing. So we're going to look at a few different methods of doing that and how we get the fuel to the combustion chamber. What we've got here at the moment, I'll just change that. I've got a graph here, a little display, and what it is, oh, is Chris going in? What it is, we've got a rail of fuel burners. Now these are represented by the green ones here. The yellow ones, they're just exploded, the bigger versions, to show you what's going on inside. And depending on the type of engine, you could have 8, maybe 10 burners going round the combustion can or whichever type of combustion system you've got. In this one, we've got what's called a duplex system, where we have a primary fuel feed represented in red and a main fuel feed. Okay, and we've got what's called a distributor valve, and I'll explain what that is in a minute. Excuse me. Distributor valve, when we start an engine up, obviously, as we said yesterday, the airflow isn't going fast enough, so there's no point putting all the fuel in straight away. We'll just flood the engine. So the primary fuel is a small amount of fuel, which is enough to get the engine started. And then once the engine is getting fast enough, we can then put the rest of the fuel in according to the speed of the engine. And this type of system we've got here, we've got a little distributor valve. It's just a little mechanical valve. It's on a spring, calibrate spring, which will open once the pressure in the main system gets sufficient to overcome that valve, and that will allow the fuel to join in with the primary one. Now, obviously, gravity is a big thing here, where the fuel will try and start on the bottom burners of the engine, and then eventually when the pressure builds up, it will join the top, and that's why we have distributor valves in there, where it will allow the fuel to go around the outside of the main line, but it won't let it join in until that pressure builds up sufficiently enough. And that's done by the fuel pump, which is attached to the gearbox, which will spin in time with the gearbox and that sort of thing. Okay. Now, as we get the fuel going in there, we need some sort of regulating valve or pressurizing valve to maintain that. And the distributor valves, somebody else coming in. Push back. Okay, so we need to maintain that pressure in there. Now, again, as I saw the previous diagram, we've got in red here, which is the primary flow, which is always open. Okay, it's always ready to go to the burners. And then the main one, let's say we've got a little pressurizing valve, which can be calibrated. We can adjust the tension on that spring to increase the pressure or decrease the pressure before it actually activates. And simply, we've got an shut-off cock there, the HP shut-off cock, just an open and shut valve, which is operated by the pilot or yourself, the engineer, and that will maintain the correct pressure. Okay, depending on the system. This is the older mechanical system. So basically what we say is it ensures enough high pressure in the primary fuel flow to provide adequate atomization at low fuel pressure. So basically we're trying to put enough fuel in there at the right pressure, but again, not too much where we actually flood the engine. Some of your old motorbikes, I'm sure will have the chokes on them. So basically it's like a choke. We don't want too much fuel in there. We want some fuel in there, but we don't want too much fuel. So I mentioned already distributor weights. So we might have the distributor weights version, which is automatic, or a single pressurizing valve with a valve within itself to distribute at the appropriate time. Then once the engine's self-sustaining, the main valve will be open all the time, and then it's up to the throttle to induce more fuel or less fuel appropriately. But once the engine's self-sustaining, the prime will be open as always, and the main will join in, and it will stay open and provide enough fuel as and when. Okay, so it says the primary fuel flow will not have any weights in. We don't need any distributor weights because you'll find, I don't have a picture of one, I should get a picture of one actually. If you look at an engine that's got a duplex system, as we call it here, a primary and a main feed, the primary tubes are always the smaller one. The main fuel ones will be the bigger tubes or the bigger pipes. And the reason for that is there's more volume. So, primary, you just need a little bit of fuel, so yeah, enough to get going, get started. And then obviously once the engine's up and running, you can get more fuel, so you need more volume of fuel, so hence the bigger pipes. Occasionally fitted to ensure there's adequate working pressure in the fuel control systems, in which case it might be renamed what is called or known as a back pressure valve. So pressurizing valve may be something that's put in there, and it's sometimes called a back pressure valve. Okay, just worth maybe making a note of that. And where there's either a single fuel flow or a partial double fuel flow, it might have one of these systems. This is more for an older system. The newer electronic ones are slightly different, but this is just a basic sort of fuel setup to look at. So we'll move on to the burners themselves. There. Now, as I said, there's going to be quite a few different types of burners, but there are two main types. So there's two main methods of burning. Say burning, the way we distribute the fuel to the combustion chambers. Now, first one mentioned is vaporizing. Now, vaporizing, that's where we preheat the fuel. So when it goes in the combustion chamber, it's almost like a steam. You know, it's really easy to ignite, and purely by the heating of it, the slight spark and off it goes. Okay, so it's more like a fume compared to an atomization. Another one is the atomized, like a spray. Think of a shower head. When you're in a shower, the water's coming out of the shower head and sort of droplets. Well, on a burner, it's an atomizer. It's the same sort of thing. Very, very fine droplets. It's not a steam. It's not preheated. It's just a very fine spray. So the two main methods are vaporizing and atomizing. I'm looking at a few different types. So we'll start with the vaporizing type. Now this one, as I said, if you look here, there's a combustion can, but we'll come to combustion cans in a minute. And the actual burner is also known, because of the shape it makes here, it looks like a hockey stick. So we call it a hockey stick. Now, this would be the front of the engine, and obviously over here would be the back of the engine. So the burner actually faces towards the front. Now, normal burners would face in line with the engine or to the back, but the vaporizer tends to face forward. So it's the reverse of like a normal burner. You can see the vaporizing tube itself, and say it preheats the fuel. So the fuel comes out preheated. As it comes out, it turns out a very fine mist. So when we add a spark, it's very easy to ignite. These type are quite prone to build a lot of carbon, and you can give a hot spot. So when you are inspecting these using a borescope equipment, be very careful. Make sure that the ends here aren't getting blocked up in that as well. Okay, and prone to cracking as well. So that's your vaporizing type. So vaporizing, preheat, known as a hockey stick. That's pretty much what you need to remember for that one. Atomizers, as I say, they spray the fuel out. Now, we'll jump ahead a little bit. Most atomizers, depending on the type, when you change one, you don't just change one on its own. You must, if there's 10 burners in the system, you would change all 10 at the same time. Now, just like cars, I keep using cars and motorbikes as reference because I'm an ex-mechanic myself. It's good to try and relate it to everyday usage. Somebody else come in, set it up. Your diesel cars or your lorries, your HGVs use injectors, and even your petrols use fuel injection. Now, the injectors, they spray the fuel out in a certain pattern. Now, these injectors, and indeed the burners for the jet engines, will be at manufacture. They will be put into a test lab. They will have fuel sprayed out at certain pressures, and they must make a certain shape. And you see here at the top here, we've got a low pressure, cause a continuous flow of fuels from, we call it a bubble. It looks like a bubble. At intermediate pressures, the flow begins to break up. So it's, you know, it's like a garden hose. You twist the hose, you can make different shapes on the garden hose, and eventually at high pressure, we get like a shower head sort of formation. Okay, a finely atomized spray. Now, as it goes through its manufacture process, these spray patterns will be unique to each burner. And what the manufacturers will do is ensure they supply, let's say, with 10 burners in an engine, they will supply 10 burners which have or should have exactly the same spray pattern. Because imagine if you've got maybe 5 burners that are given a nice spray pattern at high pressure, but maybe there's a few doing this, well, that's not going to work very well. We want all the burners to be producing the same spray pattern at the same pressure at the same time. So if you do have a faulty burner, it's maybe really carbonized up, you can't really clean them because they're very delicate on the tips. If you take one out, you must replace them as a complete set, so make a note of that as well. Always where possible. You can get concessions from manufacturers where it could be inability of spares. They will give you concession to replace one purely because there's no spares available at that time. But ideally, always try and replace them as a complete set. And a variation of what you might come across, this one's a simplex, means single. Okay, so basically you've got the fuel coming in through the tube and goes through, and you can just see here we've got what's called a screw thread filter. It's basically, it's also another name for what's called a last chance filter, and we use the same principle in oil systems, which we'll come on to later. This is a very, very, very fine gauze filter, because you'll have filters in your system anyway, but this is just in case some small bit of debris has managed to get through the system. Maybe a pipe's been disturbed in between the burner and the fuel pump for whatever reason, and maybe a little bit of debris got in there. The last thing you want is debris going out the nozzle. The nozzle is very, very small because it's got to make that spray to get the fuel into the combustion chamber. You also have air, a little tapping of air going in as well, and that helps mix up with the fuel, make a good recipe, and help spray it into the combustion chamber. And take a tapping from maybe the bypass or something like that as well, or even maybe the back of the the compressor, sorry. And that comes out as a single point and then sprays into the combustion chamber under the correct conditions. And that's a simplex. So the one we're getting after that is, strange enough, 2, which is called, pretty much like the first diagram saw already, where I had your primary feed and your main feed. It's just a twin version of the simplex one, but we call it duplex. Duplex for dual. Okay, so same again, you've got your primary fuel flow coming in, just like we saw in the previous diagram. But we've also got the main fuel flow. Now remember, that won't open unless we've got a pressurising valve or a distributor weight, once the engine is going fast enough to overcome the pressure. So the primary will open first. And again, we've got a last chance filter in the primary. We don't really need it in the secondary. Okay, so the engine will start with the primary feed being open. You can just see the rings here. Okay, and then the secondary, obviously, that will open once the distributor weight or the pressurising valve is activated. And again, you've got airflow coming in to help with the mix. Now the airflow obviously does 2 things as well as mixing with the fuel. It also helps prevent carbon buildup. You've got a fast moving air going over the extremity of the burner there, so it helps prevent carbon sticking. Because imagine in a burner, you're up to maybe 2000 degrees centigrade. The carbon can build up with the burning and it will start to stick on the outside of the burner. You never get rid of all the carbon, but it helps prevent a lot of carbon build-up very quickly, especially when the engine shuts down, because imagine when the engine shuts down, there's no fuel, but it's very hot in there, the heat and condenses and can form carbon build-ups. By having an airflow to help mix with the fuel and also prevent carbon build-up, works very well. So you get a compressor delivery, and that's indicated by this grey sort of colour here. You can just see the grey that goes round. Okay, so it does 2 jobs: helps mix the fuel and also prevent carbon. So that's your duplex one. So simplex, one feed, duplex, two feeds, primary and main. Then I've got a rotary atomizer. As it sounds, it's rotary, it actually rotates. So fuel's fed in the centre of the main shaft and then through what's called tangential drillings. So you've got holes all the way around. In the end of the shaft, combustion area, so as it's spinning, it's throwing the fuel centrifugally. Okay, so the fuel is atomized by centrifugal action of the shaft. Not a common type now. Again, this is probably an older type system, but it's just to be aware of the different type system we've got there. You see the shaft there, and the burner's spraying it out, okay, through centrifugal action. Spray nozzle, more like a garden nozzle, okay, carries a proportion of the primary combustion air with the injected fuel. So actually some combustion air goes in it. So you've got the fuel, which is the blue, going through, okay, and then it actually induces the air into it and helps mix it out towards the spray nozzle here. So actually, as it comes out, it hits the nozzle and bounces off it into the combustion can. So that's just a spray nozzle. Quite simple, quite straightforward, nothing too hard with that one. And it also helps what we call aerate the air. So by throwing it out there, it mixes with air as usual, and by having that air fuel mix again, makes a good recipe for it to ignite, rather than just a big blob of fuel coming out. And a good one, it helps reduce the carbon formation and also exhaust smoke. And the better the mix, the better aeration, the better combustion you'll get, and the less wastage you'll get. Again, going back to cars and motorbikes, when you start a car and motorbike up, the exhaust fumes come at the back, there's always going to be a little bit of fuel in your exhaust fumes. You never get rid of all the fuel. You think so, in your combustion system, you think you set fire to it in your piston, in the cylinder, sorry, but there's always a little bit of fuel that doesn't quite get burned. So it comes out the exhaust. And you might have seen some of the films where you'll see flames come out the back of some sports cars, and maybe the Fast and Furious and that sort of thing. And what they've done there, they've put ignition or igniter, spark plug, and exhaust, which helps burn off the rest of the fuel. It does nothing, it just makes a big flame. Looks very good, sounds all right, but it does nothing to give any extra power. So you see the fancy, as we call them up here, boy racers, and they have flames coming back of the exhaust. It's all show and no go, as we call it. Okay. An air spray one, again, very, very similar to the spray one, just uses a slightly different format. At the back here, it's actually got what's called swirl vanes. They look like, to be honest, like IGVs that we spoke about yesterday, and like guide vanes. Just little ridges, supports that go all the way around in the shape of like an aerofoil in effect. So as the fuel comes down, mixes with the compressor air, it swirls out. It helps, again, it's making that mix, that recipe for combustion. And this one happens to have a distributor weight inbuilt in the actual burner as well, just like we saw in the very first diagram. Okay, again, that will only open once a sufficient pressure has come up. And that will allow the fuel to enter, and you've also got your compressor delivery. Now remember, compressor delivery air is quite hot. It's about, what, 500 degrees? So that hot air mixing the fuel helps to warm that fuel straight away, and obviously helps to ignite, make it easier to ignite. We don't want really cold fuel going into the burner. All under the correct conditions. Yeah, roughly 500 degrees to about 600 degrees for delivery air. Okay, so that's your main burners. Nothing too drastic there. Oh, somebody else joining in. Okay. Just make sure I've covered that. Again, you've not got the same books, but your old books will have these in them. Yeah, we've covered that one. That's all good there. Any questions on burners so far? Again, it's quite straightforward. It's knowing the types. Now, normally back home, we could actually take you to the hangar. We can physically show you these ones. Again, we've just got some pictures here to try and show as best as we can. So just with the types, just the main thing to remember is the difference between two types of vaporizer, which preheats the fuel, and atomizer. As it sounds, it atomizes the fuel. No preheating, but we do get the heat from the compressor delivery air to help mix with the fuel, warm the fuel up, makes a nice cloud of fuel and air mix, and then we set ignition to it. Okay. All right, any questions there before we move on to combustion cans or combustion systems? All good so far? All quiet.
Good.
Oh, good, good, good. Right, combustion systems then. So again, we're looking at the burners, and we're going to show you how the burners interact with the combustion cans and the types of combustion cans. Now, I mentioned this recipe or this mix of fuel and air. It has to be the correct mix. Like you're making anything, the mix is very, very important. If you ever do module 16, we speak of the stoichiometric fuel mixture. Okay, and that's the ideal mixture of air and fuel. And it has to be the same for combustion engines, petrol engines as well. It will vary once the engine warms up, and especially for jet engines. So what we've got is the combustion process requires, for a startup before it gets warm, is 15 pounds of air to 1 pound of fuel for complete combustion. So it's a 15-to-1 ratio. 15 parts air to 1 part fuel. Okay. Saying we call this the stoichiometric mixture ratio, but just remember the numbers for now. You cover that in module 16 if you ever do module 16. But the numbers are exactly the same. Okay, and that's known as the air-fuel ratio of 15-to-1. And what you want to make a note of is obviously 15-to-1 ratio, but it's always by weight, not volume. Okay, it's always by weight. So if you got an exam question and it says what is the fuel ratio for a gas turbine engine, they might give you 15-to-1 by weight, they might give you 15-to-1 by volume, and they might give you a random number by weight. It's always by weight. So make a note of that and highlight that where appropriate. Okay. I say that goes for combustion piston engines as well. Air to fuel can also be between 45-to-1 to 130-to-1, and that's over the engine RPM, the complete engine RPM range, over the whole RPM range. For normal startup, normal running, it's 15-to-1, but once the engine gets warm, once the engine's going at altitude, we don't need as much fuel. So the bigger the air number, the weaker the mix. So at the moment, 15-to-1 is quite a, it's a correct mix, but it's a lot richer than it is these ones. 45-to-1, 130-to-1, engine's nice and warm now. The engine, certainly here, could be up at altitude. There's less air, it means we need less fuel. Okay, so we have a higher mixture ratio there. In other words, a leaner mix. It's a very, very weak mix because we don't need as much fuel at altitude. But once it comes back down to a dense altitude, it'll start coming back maybe down to 45, and then eventually maybe back to 15-to-1. Okay, so be aware as the standard ratio is 15-to-1, but over the whole engine RPM, it can go up to 45-to-1 to 130-to-1. So again, any questions come at exam, make sure you read the question. Is it asking just for the general fuel air ratio, or is it asking for the over the whole engine RPM range? Okay, so just watch out for that, and always by weight. Okay. Now we've got a section here of a combustion can. We've mentioned that we use the bypass air, or even most times delivery air from the HP compressor. Okay, so that would be P3, delivery air. Now we take 100% of that air, or a little bit of what's called cooling airflow, and we split it up. Now we split it up into cooling air, which goes round between there's two skins of a combustion can. You've got inner layer and you've got your outer layer. So between these two layers, you'll have an 80% of that 100% we'll use for cooling air. The other 20 will help aid combustion. Okay, so basically the overall mixture is 20% for combustion, and we'll use 80% for cooling. Okay, and that's represented here by in between the skin. Okay, now we've got initially what's called a primary zone and a dilution zone. Okay, now the dilution zone is also known, maybe we can note this, as the tertiary zone. I'll see why in a minute. So initially the primary zone is about 20%, and then you've got about 40, maybe 20% mixture there. That gives you overall 80%. Okay, for cooling airflow. The other 20% gets split into 12 and 8. 80% for a bit of cooling within the combustion initial part, and 12% goes through the swirl vanes. This would be the front of the combustion can. Obviously, this would be the rear. And just to go back a bit, you can see the divergent shape here. Again, that would be down here as well. And then convergent shape on the exit of the combustion can, because once you set fire to the fuel, we want it out as quick as possible like gas. Okay, so we'll get 100% air coming in, and we'll split to 80 and 20, but overall we use 80% of the tapping of the air for cooling. Okay, 80% is used for cooling, and we're going to split this down into 3 more parts. So 3 parts are known as primary. So the first one's primary, that's for mixing the fuel, okay, and it helps to support combustion. So primary is for mixing the fuel and support combustion. Secondary, that helps shape the flame. The way to remember this one, S for secondary, S for shape. Okay, just a short way of remembering it. So secondary airflow is shape the flame and completes combustion. In other words, we've got the flame going now. Okay, so it helps shape the flame and complete combustion. Well, tertiary, that's the last one. Think that's final. Think tertiary, that's finished. So we cut the flame off. We don't actually get there with a pair of scissors and cut it, but it just, the cooling air comes round and it prevents the flame tip from reaching the turbines and the NGVs, which we'll come on to shortly. So make a note of these ones or highlight them in the book if you've got one in your old books. Primary, secondary and tertiary. And this is all 80%. Okay, that's all 80%. So we've got primary, mixing, support combustion, secondary shapes the flame, tertiary cuts the flame. All right, we'll repeat that a few times. The other 20%, as I say, gets split into 12 and 8, and 12% goes through the swirl chambers into the burner. Okay. So that's the 3 ones you want to remember there. We will come on to another primary, second, tertiary with turbine blades, but that's slightly different. But for the moment, for cooling air, you use 80% for cooling air, primary, second, tertiary. And also remember, as I said before, go back to the previous diagram, that this dilution zone or dilution air is also known as tertiary air. Okay, so 80% for cooling air, 20% towards the front of the combustion can, okay, which is split into 12 and 8. But definitely remember the primary, secondary, and tertiary airs. You'll definitely get a question on one of those. Okay. But again, we will recap these every day. Okay. Now, the secondary tertiary, again, also forms what's called a boundary flow on the inside and the outside of the flame tube, which is manufactured from resistant steel, usually what's called the mnemonic range. Okay, a good name to remember. Anything that's in the hot part of the engine tends to be, especially doing locking wire. Now, locking wire for nuts and bolts is normally stainless steel, but when you get the hot part of the engine, the exhausts and combustion chambers, we use a mnemonic type metal, very high heat resistance steel. Okay, and there's that combustion cam just said before. So there's the front, there's your cooling air coming in. Okay, and that mixes with secondary and tertiary, so that'd be at 80% fuel, so 80% cooling air here, then your primary. You have 20% coming through, which is split into 12 and 8, and then your flame, and then it goes. And again, as you can see, there's a divergent shape, so it slows the air down, last chance pressure increase, then it goes on fire, and then it comes out the back of the combustion can in a convergent shape, so it speeds the gas, so it's already speeding the gas flow out towards the next component. The air casing is normally aluminized, mild steel, so the outside casing, again, heat resistant on the inside, but aluminium sort of aluminized mild steel on the outside. But if you just had one casing, well, the first casing will get very hot, and again, that's very close to aircraft structure, so we need that cooling air between. So this cooling air, as I said before, that helps maintain a barrier, a boundary layer air, so we don't have the hot 2000 degrees trying to escape into the aircraft structure. This would be quite catastrophic. Again, when you're checking these, we'll look at 4 different systems shortly. The new systems you'll look at, they're with inside an engine. Some combustion cans actually outside the engine, back in the older days. So it's quite crucial when inspecting these using borescope equipment to make sure you take your time and make sure there's no cracks. Any cracks, well, they're going to expand as it gets hotter and potential flames coming out of that, again, with catastrophe type results. So we're going to look at type system. Now, there are basically four main types of combustion system, or four types of way of having a flame in an engine. First one is multiple chamber. The second one is tubo-annular, also known as can-annular. The multi-chamber is also called multi-can. It's another way of looking at it. The most common one in commercial aircraft is annular. It's one big combustion can, big annular can. And the last one is called reverse flow, where it actually sends the flame the wrong way, and we use that on maybe turboprop engines, APUs, and it's just a way of compacting the whole engine into a small bundle, because normally having the engine, compressor, combustion system and the turbine, but having a reverse flow system, you actually combine it above the turbine. So multi-chamber or multi-can, tubo-annular, annular and reverse flow. So let's have a look at them. So this is your multi-chamber one, or multi-can sometimes called. Now, although the cans have liners, an inside liner, outside liner, the next thing above this is actually the aircraft fuselage, okay, which will have a heat-resistant material above it. So the cans are actually external. If you have to take this whole engine out, this is just showing you the combustion cans. Obviously, we'd have the compressor and all that this side, you have the exhaust and all that this side. But if you took the engine out, you would actually see these cans. You can actually go and touch them there and then. I'll try and get a photograph of one for you. Okay, so you can see here we've got 1, 2, 3, 4, 5, 6, 7, 8 combustion cans. This is actually taken from what's called a Dart engine, fitted to Hunter aircraft, canvas, old military type aircraft. They're quite big. They're good old, I mean, probably the size of that. They're quite large cans. You can see the fuel feed connections there. And you've also got interconnecting hoses as well. Interconnecting tubes, which allows the flame to go around to each can. You've also got drain tubes as well, because you need the fuel. It might, once the engine shuts down, the excess fuel will drip into the combustion can. It needs to drip down and get to the bottom and finally back out. Primary air scoop, where it comes in from the compressor. We have something called a pig snout, just for the shape of it. Okay, so that's your multiple chamber, or sometimes called multi-can. All right. Just see around here, there's a big seal, a fire seal, because it's bad enough we've got hot combustion cans very close to the fuselage, and if there potentially was a fire, we don't want the fire coming back the way. And then this part here, that would bolt on to your exhaust system and turbines and that as well. Okay, so it's a multi-chamber or multi-can. Now the next one, the can-annular, is basically the same sort of thing. This one's actually back to front. Well, it's actually the same sort of way, but just think of it as a multi-chamber, but with a can covering it. It looks pretty much the same, except this time you can see we've got a casing actually covering the cans, or the chambers. Okay, so you won't actually see these until you take the casing off. All right, so it's basically a multi-chamber, a multi-can with a can. Okay, pretty much the same sort of thing. Now this one does show you the nozzle guide vanes, and now the nozzle just sort of jumping ahead a bit. Once the flame comes out, the first thing it hits or goes through is the nozzle guide vanes. Now nozzle guide vanes are the hot equivalent of inlet guide vanes. Now inlet guide vanes, remember from yesterday, that directs the airflow onto the compressor at the correct angle. Now nozzle guide vanes, they do the same thing, but they direct the airflow onto the turbine rotors at the correct angle. But this is the hot part now. So nozzle guide vanes are hot, IGVs are cold. But in essential, they do the same job. They both direct air at the correct angle. Okay. So a tubo-annular or can-annular is another name for it. Right. Again, you've got your intake. You can see the divergent shape going in. There's a cross section of the combustion can. You can see the swirl vanes that we saw earlier. The flame tube, inner. You just see the inner layer and the outer layer. All right. And dilution holes and all that good stuff. Okay. So we'll just move on to the next one. And then the annular one, as it sounds, it's just one big can. Okay, one big huge can, which is pretty much the same size as the size of the core engine. So there's no multiple cans, just one huge big ring of combustion can. And that's the main type you'll probably come across now. All right, so there you go, HP compressor, outlet guide vanes. Okay, which again, just like inlet guide vanes, but this time they're outlet guide vanes. Then you've got your large inner combustion casing. You'll have the fuel spray nozzles, the burners going in. And now there will be burners all the way around. Just because it's one big can, it doesn't mean there's one burner. There will be at least maybe 8 to 10 burners going around. Again, dilution holes, etc. And then eventually, again, you can see here the nozzle guide vanes. Yeah. So the flame will come out, go through the nozzle guide vanes, and then that gas will go into the first stage of the turbine rotor. So this is the back of the engine. I'll say that would be the front of the engine. That's angular. So one big, huge can. And finally, we've got the reverse flow. As it sounds, now this example, the reverse flow tend to be turboprops or APUs. This is probably an APU type version because we've got a centrifugal compressor. So that shows you the air coming in and it getting thrown out radially, or by centrifugal force, through what's the next component called after a compressor before it goes to combustion chamber? Anybody remember? So the compressor, this component, and then combustion chamber. What was this component in between called?
Diffuser.
Diffuser, good, yeah. So diffuser, divergent in shape. Okay, slows the air down, last chance pressure increase. Then it goes into combustion chamber. As you can see here, well, there's the burner, in this case the vaporizer. So it's a vaporizer, it's preheating the fuel. So it's facing, now because, it looks weird, because the combustion can is back to front, it means the burner is also back to front. Okay, so it's actually facing the back of the engine this time. So the flame starts and then goes towards the front of the engine, hence why it's reverse flow. And then it will flow eventually into your nozzle guide vanes and then hit the turbine as well. Now, as you can see here, by having the combustion can above the turbine, we can compact the engine into a nice smaller space. So small space, auxiliary power units are potentially turboprop aircraft as well. Not always turboprop, but certainly APUs. Okay, hence why it's called reverse flow. It's more for space limitation. Otherwise, you'd have your nozzle guide vane section and your turbine connected to the back here. So that elongates the engine. Okay. Now, with the different types of combustion cans, the different liners, different types, you will have cooling airflows on the outside of the skins of the liners. And we've got a few different types. We've got corrugated strip cooling, so you can see here is a corrugated, just like a roof lining. You see the corrugation, the air goes through it, and that provides a film of cooling as your flame tube. And you've got machined cooling ring, which actually, as it sounds, machined. You've got drillings, calibrated drillings that allow the air to flow through there. Then we've got sort of the same sort of thing called splash cooling strip, where the airflow goes over the holes and induces the hot air away into the cool air. And then you've got what's called transpiration cooling, which is a lot like a lamination, like a lot of roads within 2 layers of a material. Okay, so it's four different types: corrugated, machined, splash, and transpiration. Just a few different types of the cooling air that goes through the skin. Having laminated and ways or means of making a boundary, all the air is doing there is making a boundary between the very hot gas and the skin of the combustion chamber and eventually to the skin of the fuselage. And depending on the combustion type, the can will depend on the type of cooling. These ones here, these tend to be for the older types, like your multi-can, multi-chamber ones. More splash cooling, and certainly this type machine cooling, that may be more for maybe your annular type cans. And that could be a mixture of both on this one here. Okay, so just be aware of these ones. 4 main types there. Okay. Again, it's just apologise you don't have your book at the moment. Right, what we'll do, we'll finish off this last bit and then we'll go for a break. And we'll move on to turbines after this. So cooling air ensures that the flame is not distorted. We want the flame to be correct shape, correct length, and not going all over the place in the combustion can, because if it does that, it will provide hot spots. And the hot spots eventually to fatigue, cracking, and then eventually flames coming out where they shouldn't be coming out. Pressure drop across the liner maintained at a satisfactory level at all operating ranges of the engine. Yeah, so we maintain a pressure drop, that boundary layer air, that doesn't matter what the engine's doing, we'll have that appropriate pressure drop for the differential pressure there. Okay. Unfortunately though, we have some byproducts of all this hot flames and gas coming out. See those smoky engines, lots of carbon, which is not very good for the health and certainly not very good for the environment. Okay, good old B-52s there. So combustion efficiency in most gas turbine engines at sea level is actually 100%. Okay. Yeah, I'm checking that. Okay. Sea level, high dense air, so that's when they're most efficient. However, byproducts, very harmful, and you will provide carbon monoxide. Well, you don't want to breathe that in because it'll kill you. Smoke and hydrocarbons, again, not good for you. Okay, so unfortunately, we are trying to get to a cleaner environment. We're trying our best. They're trying to produce, you probably heard about some of the news, the various types of engines they're trying to make at the moment. Okay, trying to make it 100% clean. It'll take a while, I think, but at the moment we've got to use, obviously, what we can. With advanced fuel combustion technologies, these emissions will gradually be reduced till zero emissions. Could take a while, I think, might not be in my lifetime, but they are trying to get there. Okay, so unfortunately, we do have byproducts. Okay, that's a good point to stop. We'll move on to turbines after tea break. Okay, so any questions before we move on to tea break? Nice and easy so far. Now the gas is coming out of the combustion system, and it's going to start spinning the turbines. Remember, the turbine is connected to a shaft and connected to the compressor, which will draw the air back in. Okay, so let's look at the turbines themselves. And the purpose of the turbine is to transmit the force of the gas coming out, as I say, into mechanical power. Okay, so the faster the turbine's going, basically the faster the compressor's going. The faster the compressor's going, the more air is getting drawn into the engine, and we can add more fuel appropriately. Again, all controlled by mechanical means or computer, FADEC, and that sort of thing as well. So look at different types of turbines, shapes of the blades, but basically it does the same sort of job as a compressor, but it's just in the hot end. It's using hot gas instead of the cold incoming gas. Okay. So again, turbines come in various shapes and forms, but its primary role is they go through a lot of stress, and turbines are actually the least life item on an engine. In other words, they're going through the most amount of stress. They've got centrifugal action going on. They've got the heat stress going on. So these modules, sometimes called a module turbine, they will be replaced more often than most components, or the big components certainly in an engine. So say an engine has got maybe 1,000 hours of life on it. Within that, maybe the turbine has got maybe 500 hours life. So the engine would come out, turbine will be replaced, and then go back into service again. That all depends again on the type of engine got fitted. Now, the turbine blades are exactly just like a compressor. They are aerofoil in shape. They will have a stagger angle on them as well, the twisting like we saw yesterday. But at this time, instead of being divergent in shape, they're obviously convergent, because we want to converge the blades together to expel the gas out towards the exhaust as quick as possible. And again, depending on how many stages, if it's a 2-stage turbine, a 3-stage turbine, or even a 4-stage turbine, we need to extract as much energy from the gas, so we're using it as much as possible. And remember, yesterday as well, we also spoke about that usually a turboprop engine will tend to have more turbine stages than a general gas turbine engine. Okay, a good one to remember there. The reason being, it was said as well, is because we want to extract more energy to help propel that propeller that's attached to the end of the shaft. Now what I've got here, I've got a diagram of the turbine blades, or the shape of them. If you look at the tips of the blades, like side on, you'll see that we've got 2 types. Now we've got an impulse one, which is this one here, and it looks like a big smiley face. Yeah, same sort of big smiley face going on. Just get a C shape, a cup shape. And we call that impulse. Now the gas which is coming out from these fixed veins, the nozzle guide veins, the gas comes out. Your combustion chamber will be over here. The gas comes out of the combustion chamber, goes through the nozzle guide veins. And as you see, they converge, so it speeds up the gas. The gas will then hit the impulse turbine, direct impingement, so it's just hitting it and get the rotor spinning. Now, these type, we're not bothered about as much as efficiency. We just want the gas to hit the turbine and spin it as fast as possible. That sort of turbine, again, would be maybe for a starter motor or an APU. We just want to spin as fast as we can. We're not too bothered about efficiency. Okay, so this first one is called an impulse turbine shape. Looks like a happy smiley face. Now the next one NGVs are still the same. They're still an airfoil shape. They're still converging. But this time, the turbine blade is more of an airfoil shape, and we call that an impulse reaction. In other words, again, like a wing, like we saw with compressor blades and the wing of an aircraft, we're extracting as much energy from that gas right along the shape of the blade itself. So it's an impulse reaction. We're extracting that energy as much as possible before it goes on to another set of NGVs, another set of rotors, another set of NGVs, and so on. And that's the type you'll see pretty much standard on all turbines in a gas turbine engine. Okay, so this type tends to be more APUs and maybe air starter motors. Impulse reaction, I always give a nickname of a Nike, you know, the Nike trainers, or Usain Bolt, that sort of thing. Just a way of remembering. Any way you can remember something. I come up with some crazy analogies sometimes, but again, whatever you want to use for yourself. So happy smiley face, okay, for impulse, or a Nike tick for impulse reaction. Okay, that's the two main shapes or profiles of turbine blades. Now, the primary factor that limits the amount of power a gas turbine can produce that can be taught is the turbine inlet temperature. In other words, the temperature combustion chamber, roughly anywhere from 15 to 2000 degrees. Well, the NGVs have to be able to stand that temperature. If they can't, then they're not going to be good for the job. So the better material, the more temperature we can produce to the turbine, okay, the turbine inlet temperature, the more power, more energy we extract from that gas, and the more efficient a turbine will become. So that's your primary factor. Once the amount of power a gas turbine can produce is the maximum temperature the turbine can withstand. Okay. So you see there's velocity. So there's your NGVs and nozzle guide vanes. Okay, the pressure's going down because velocity has gone up. All right. We will drop a bit of velocity purely by the fact that it's hitting it, so we're losing a bit of energy. But again, because they're convergent shape again, it will slowly rise up again. Okay, so we do a little bit of pressure, we do lose a little bit of velocity, but the next time the gas goes through to the next set of NGVs, the NGVs speed it up again onto the next stage, and then eventually into the exhaust. Okay. That inlet turbine temperature we call TIT, or turbine inlet temperature. We'll also have the back of that, which will be TOT, turbine outlet temperature as well. So basically, if that was a single stage turbine, we'd have the turbine inlet temperature here, and then as it came out, it'd be the turbine outlet temperature. A lot of abbreviations, and we'll cover some abbreviations later. Okay. There's more than one turbine stage. It may also be cause to consider the temperature between each stage as well. The more temperature you can retain in there, the more energy we can transmit to the other one. So if you've got temperature in between each stage, so a set of NGVs and a rotor, that'd be a stage. So the next temperature between that, it's intermediate, it's in between. So we call it ITT, inlet interstage or intermediate turbine temperature. So TIT, ITT, TOT, and depends how many stages you've got. Lots of abbreviations. When you work in the aviation world, you don't speak in normal sort of language. You speak in abbreviations a lot of the time. Okay, I'm sure you've come across that already. Turbine assemblies, again, all depends on the type of engine we've got. You can have a twin stage, single spool, twin spool, triple spool, and so on. Yeah, that same goes for the turbines. Again, you'll have your turbine shaft, which should be connected to your compressor, depending on which compressor it is. Your combustion chamber discharge nozzle, so up here would be the combustion chamber. And there's your combustion chamber discharge nozzle, which is obviously convergent, which directs the airflow. You can just see here, there's your nozzle guide vanes, again, down here. And then this one we've got shown here, this is a 3-stage turbine. So we've got 3 sets of turbine rotors. There's the back one, there's another one, and there's another one there. So a 3-stage turbine. And this just happens to be one shaft, okay? So it's just a single spool, 3-stage turbine in this case. And then in between there, you'll have exhaust mountings and NGVs in between. There's NGVs there. Okay, so 3-stage turbine in this case. So one shaft, but 3 stages of turbine. So again, that could very well be a turboprop aircraft, more stages of turbine on there. Okay. Twin spool, we're going to have 2 sets of turbines, 2 shafts. So you can just see here, the outside shaft is your high pressure shaft, and the smaller one inside is your LP shaft. So your twin spools, your LP spool and your HP spool. And remember, the turbine you see from the back, which one will that be? Will that be LP or will that be HP? If I'm looking at the back of the engine, the first turbine you see from the back of the engine, what's it going to be, LP or HP?
Always LP.
Always LP, yeah? Always LP. Now we've got a single stage, oh, something else coming in. So a single stage HP turbine, okay, so just one stage there. And we've got a 3-stage low pressure turbine. So you can just see slight difference. Although we've got a twin spool engine, we've got a single stage HP turbine, but we've got a triple stage LP turbine. So again, it all depends on the type of engine and what the requirement is. So don't expect that all the turbines will have the same amount of stages. It just depends on the type of aircraft. It could have a single stage per spool, might be 1 turbine per spool. Like we've got there, we've got 1 turbine on the HP and we've got 3 stages of turbine on the LP. It just all depends, as I say, on the type of aircraft. And what to do. Ideal triple spool. So again, there's your HP shaft, that's the big one there. Then your intermediate shaft, and then the one inside is your LP shaft. Okay, so again, low pressure turbine at the back, and this is a 2-stage one. Then your NGVs, then you've got a single stage intermediate, you can just see it about here, and then your single stage high pressure at the front, which would be small. So the biggest at the back, and then smallest towards the front. Yeah, so single stage, intermediate, and your LP. Okay, all compact. And again, all depends on what that engine's being used for. Power or free turbine. Again, you can call it a power turbine or free turbine. This will be for your turboprop aircraft, but the same principle applies. There's your free turbine. Okay, free turbine shaft goes through to a reduction gearbox, and then your propeller or power output shaft, it could go to a different gearbox, so it could be a turbo shaft engine, which we'll come on to, but we'll take this as being a turboprop one. Now remember, a power turbine or free turbine is not mechanically coupled. It's only the gas coming out of the engine that propels the turbine. There's no gears that actually move the turbine. The turbine is free to move on its own. Okay. The reduction gears, that's just the reduction gears for the propeller for the speed, but physically the core engine does not propel the turbine. It's only the gas from the actual core engine that's propelling the turbine. So there's no gearing. It's unlike a fixed turbine. Okay, such a free turbine. And we'll come on to reduction gearings shortly as well. Okay. Again, you can see NGVs and your turbine blades at the back there. The turbine efficiency, losses which might prevent the turbine from being 100% efficient. Now, we'll never get 100% efficiency. We get close to it, and obviously better materials can make it more efficient. But again, due to a number of reasons, aerodynamic losses at the turbine blades, yeah, we'll never get to use all the air, unfortunately. We're going to get turbulence from as it gets over the tips or the sides of the blades or around the blades, and as it's spinning through, we get aerodynamic losses, just like you do on a wing on an aircraft. Again, aerodynamic losses at the NGVs as well. So even the air, as it hits the NGVs first, before it gets to the turbine blades, we've already encountered some losses. Gas leakage over the actual rotor blades as well, the tips. And we'll look at controlling that a little bit better as we go through the book. And we'll also get exhaust system losses as well. So we lose a bit of energy here and there between certain parts as we go through. Example, we've got percentage losses in your book. Now, you don't have the book there with you, but I'll read it out to you. Give you an example of how much you've got. You might have it in the book, I can't remember offhand, but you should have what would be in page 80 once you get new books. It gives an example of a typical 3-stage turbine would suffer a 3.5% loss because of aerodynamic losses, turbine blades, etc. A further 4.5% loss being incurred by aerodynamic losses on the NGVs. So I might actually put these up in here. So 3.5%, 4.5% there, and other aerodynamic muscles over there, and you'll get an overall loss and efficiency would actually result in it being 92%. Okay, that would be on page 80 of your new book. So it's not bad, 92% efficiency, better than 50% obviously, but unfortunately we never get 100% efficiency. As much as we try and get there, you're always going to lose a little bit of energy somewhere along the line. But we try and better materials, better shapes and that sort of thing. Again, diagram there, you can see the shape of the profile of the turbine with NGV is your impulse reaction. Okay. The important thing here is what we call compressor turbine matching. And it's basically the flow from the compressor and the flow of the turbine. Provided we don't have too powerful compressor or too powerful turbine that's not restricting or increasing the flow, as long as they're matched properly, we'll get the right amount of flow from in to the right amount of flow going out. If that changes somewhere through damage or mismatching, it could cause a few problems. So the flow characteristics of the turbine must be carefully matched with compressor to maintain the efficiency and performance of the engine. Example is, if the nozzle guide vanes allowed too low a flow or too low a maximum flow, then a back pressure would happen. And that would build up, causing the compressor to surge. In other words, you're getting reversal of airflow. We're choking the air. We're going to build the pressure, and that only place can go is going forward. So nozzle guide vanes, basically, if they're designed they're too small or the gap's not enough, it's restricting that flow of the hot gas coming out to the turbine. So if it's restricting, you're going to get back pressure, and it's going to go back forward through towards the compressor. That'll slow the compressor, potentially stall the compressor. You get a surge, and a good sign of that is the good old rumbling, vibration, EGT, RPM gauge, failure to accelerate, and potentially flames coming out the front of the engine. We're not very good. Again, worth making note of this. A question might come up in an exam of something related to this. So nozzle guide vanes too low a flow. Again, back pressure, potential surge. On the opposite side of that, too high a flow would cause the compressor to choke. In either condition, a loss of efficiency would occur rapidly. So again, if the nozzle guide vanes were too much a flow, it's coming out too quick. It means there's more air coming in the compressor can handle because the turbine's going quicker. The compressor going, I can't cope with that. So the air in the compressor, even with the bleed valves, is too much. It'll end up choking the compressor. Now, if it chokes the compressor, same again, you could potentially stall the compressor and basically an engine stall. Okay, and potential flame out, because if it can't go through quick enough, then it can't cope in the combustion chain. It'll probably flame out and stall anyway. So two ones to remember there: too low a flow, potential surge; too high a flow, compressor choke, which will lead to stall. Okay, so make a note of those. Turbine disc, again, is machined forging with a flange onto which a shaft will be bolted. We'll look at different ways of fitting the blades and the shafts together as well later on. Now, the disc is manufactured from a high heat resistant material, again in the Nimonic range. Nimonic is a very high resistant steel, okay, or alloy steel in this case. It's got to withstand those high temperatures. That disc might be taking on about 1500 degrees C, which is obviously very hot. Okay. Turbine blades themselves come all weird and wonderful shapes, and all the types used to be sort of different materials. Nowadays, we're going from what's called a single crystal, but they go through a lot of stress, a lot of heat, expansion, contraction, they heat up, they cool down, they heat up, they cool down. Okay, plus the force of the air hitting them, impinging on them. They go through a lot of abuse, shall we say. All right. Now, the cooling, also want to keep these cool. I can see some of these ones, going back to this one here, you can see these tiny little holes. Okay, and depending on the shape, these help guide the airflow around it. Now we can use cooling air. Now some of the turbine blades, like the older one here, were just solid blades. Some of the newer ones, like NGVs, have actually got holes within inside them, which allowed cooling air to go through the middle and evacuate out the back of them. All right, as can be seen here. This one's classed as what's called a single pass, where cooling air comes in, goes in between the blade. You can just see these little holes and the exits out the back end. Now, the air going inside, that helps keep it cool inside, and then the air going around outside causes a boundary layer air. So it helps keep that really, really hot, intense gas from burning away at it. Multi-pass one, as it sounds, got air coming in, it goes all different ways. It comes out the front, it goes out the trailing edge, comes out the middle, and that sort of thing. So that's a multi-pass one. And then I've got ones that's got a thermal barrier coating. Again, you can see the profile shape of the edge of the blade there, and probably hard to see in the diagram, but the colour, that sort of bluish violet colour, that's your cooling air. Okay. Now that's great. It makes the blades lighter because you've got the drillings in the blades as well, so we can go faster. But it's also prone to potentially hot spots. So any carbon that builds up maybe blocking the holes. But if it blocks the holes, then it can't cool. If it can't cool, it tends to erode. So you can get quite a lot of erosion. So you have to make sure they're clean. On the trailing edge, all these holes make it very brittle. Again, so they can potentially start fracturing and break off as well. Okay. And we'll come on to the shape and how we hold the blades in position. You can see the shape, got these lines, sort of V shape. We call that a fir tree root, and that's how we fit them into the disc. And the reason we have more than one serrated edge is that spreads the load as it fits into the disc. That little 2-ounce blade, if it's a 2-ounce blade, potentially just like the other blades, and the centrifugal force can cause it to be about 2 tons of pressure on a small little blade like that. So as I said there, fitting these blades is we call the fir tree root. If you think of about, certainly we've got them here, not maybe much in Nepal, but the fir trees we've got here, like Christmas trees, and you get the pointy shape tree going on. Well, it looks like a tree upside down, and that's what we call a fir tree root fitting. Okay, so it's slot in position and sideways, and those every little layer going up, as I said, that spreads the load of the centrifugal force. If you just put one layer in there, then all that stress would be in one little layer, which is not useful. But having these smaller to gradually bigger layers or ridges, okay, these ones here, that helps spread the load of the force through centrifugal action. This type is similar. We've got a fir tree root with shank seals, just a slightly different version of the fir tree root. So that's, again, a common question would be, how do we attach blades to the disc? By fir tree root shape or design. Okay, if you want to know it. All right. Now you can see just a little graph of the stresses and the heat that's going through some of the blades. Okay, and the stresses. So hot points through the middle, tends to be the middle. As it tips, getting the high velocity gas going back, but sitting towards the centre, it's a little bit cooler. Again, a lot of heat, certainly in the middle area of the blade. So a lot of corrosion and erosion can happen in the middle. So a lot of stresses. And again, obviously stress, you've got stress at the root, you've got stress at the tips. So a lot of stress with the centrifugal force is happening. And as the blade gets thinner, a lot of weakness goes on as well. Now, we mentioned in the fuel system with the primary, secondary and tertiary cooling air. Remember, primary was helps initiate combustion, support the flame. Secondary shapes the flame, and tertiary cut off the flame. Well, we also use the terminology for primary, secondary, and tertiary to reference the stresses of the turbine blade. Now, as you can imagine, the turbine blade is going through centrifugal force, so it's trying to pull away from the disc. So through a time, when it's brand new, it needs to bed in. So when we start spinning it up, what we mean is it's going to stretch through its lifetime. All that force of it trying to pull away all the time, it will eventually stretch the blade to a point. Now the first one, the primary area, that will be when it's brand new, it's been in a test bed, and it's going to stretch. It will stretch so far, and then it will settle down. It'll go, okay, I'm having a bit of a stretch, and I'm okay now, but I will continue to stretch through the rest of the life of that blade. The secondary part, that is when it's actually fit to the aircraft, or usually, where manufacturers have done testing all these blades. They found that the blade will stretch quite quickly initially in the primary zone. It will then be sent to the engine, fit to the engine, and then this secondary part is the life, the actual guarantee that when it's fit to the engine, the aircraft's flying, however many hours that is, depends on the blade, depends on the engine. It's going to stretch up to a certain point. Up to that point there, this is what's going to life that turbine blade, because they know after this point here, it's going to potentially fracture and snap. So a turbine will stay in an engine, all this point here, the secondary point, up until a certain amount of hours where it will be removed because they know at a certain amount of hours there's a good chance it's going to stretch too far and snap, which is now the tertiary point. Okay, very, very rarely you'll get concession from a manufacturer to keep that turbine in the engine if it's gone past the secondary point. It might be there might have been a problem with the aircraft. It's maybe landed in a different country somewhere. It needs to fly back. They realise that the turbine is very, very close to the tertiary area. They might give a small concession, maybe 10% an hour, maybe enough to fly it back, provide the flight, undue stress is required. But normally, the normal flying period is a secondary point here. Through tests in the manufacturing process, they know that at a certain point, a certain amount of hours, that blade will potentially snap, and we don't want that to happen in normal flying conditions. So as I say, we will remove the engine and replace the turbine. Hence, the turbine is the least life items, the smallest amount of hours against that engine. So we don't want to be flying the engine with a turbine that's in the tertiary hours. Okay, so primary, rapid stretching, then it settles down. It's like primary's like a bedding in point. Settles down, that's where we'll fly the aircraft, no problem at all. We can guaranteed so many hours, that turbine in theory should be okay. Saying that, sometimes it does snap. One of those things, a heavy landing can put a bit of a shock onto the turbine blade, which might reduce the amount of secondary hours available. But again, it's very hard to distinguish that. They do happen, some blades do snap before the tertiary point. That could have been a fault with the process of manufacture for the blade potentially. But definitely, we don't want to be flying any engines with turbine blades in the tertiary zone. Okay, so primary, secondary, and tertiary. I mentioned that materials are an important factor of the turbine blades. Early ones, we were called equiaxed or equiaxed type structure. Now, if you have to go into a microscope and check these blades, they had a lot of grain or granular structure to them. Now, any granular structure means it's got boundaries. Well, boundaries in a granular structure is a weakness. Okay, so in a turbine blade, that's quite crucial. So early days, you would find a lot of blades would snap and crack and not last as long. That was a crystal type structure. Then they moved on to what's called directionally solidified structure. So they've still got the grains within the material, but they're going like in line with each other. So yes, we've still got weak points, but they're not all over the place like this. They're actually going in line. So it's slightly better, a bit more improved. Nowadays, all blades are called what's called single crystal. They actually grow the blade. Now, I don't mean they put it in the ground as a seed and grow it. It is a chemical process. That is a special process. I've been lucky enough to go down to a Rolls-Royce factory and see these blades being produced. However, they won't show you the process of actually how they grow the blade. It's a very secret process, patent process. Okay, but as you can see there, there is no granular structure. It is grown from one single crystal. Okay, so there's no weak points in there as such. Very clever process, very secret process. Okay, so this is what most, certainly nowadays, and they're content to improve that. Even on this type of structure, they're still content to improve that type of process as well. Okay. So looking at the difference between the three of them, there's your equiaxed blades. Again, the time you got for one of those, the time the primary, second, tertiary creep, compared to a single crystal, well, it's almost triple, maybe 4 times better compared to a single crystal, yeah, before it actually goes. The direction solidified, yeah, it's slightly better, but certainly the single crystal blades, it's at least double, as efficient as the equiaxed blades. Okay. That's just a representation of the 3 types there. Okay, any questions on what I've covered there so far? All good? Right, I'll do a little recap before we go to the exhaust section. And then once we've done that one, we've got thrust reverse, so a noise reduction, and then that'll be that bit. So we'll just go back away a little bit, a couple of questions, and we'll go for a quick break again, and then we'll move on to the exhaust system before we go on to book 2. We'll try and save that for a little bit later on. Right, so explain to me, with reference to the turbine blades, what primary, secondary, and tertiary was? Francois? Okay, so you're exhausting there. Get your microphone on. Oh, Consider.
Yeah, I'm here.
Yeah. What do you think? What does primary, secondary, tertiary mean with reference to a turbine blade?
Primary airflow, you mean primary and secondary?
No, primary, secondary, tertiary with reference to a turbine blade. We do have primary, secondary, tertiary for airflow, but what does primary, secondary, tertiary mean for a turbine blade?
Initial creep are primary.
Thanks, Rob. Yeah, initial creep, secondary creep, and tertiary creep. Yeah. So which one of those?
Yeah.
Yeah, which one of those do we normally fly in?
Primary.
Primary.
Yeah, I mean, it might be. Usually they'll have been bedded in already. They'll go on a test bed, and then the engine will be sent out to the aircraft. And so the turbine blade should really be, once it's been tested, will be fit to the engine, and then we'll get an engine for the aircraft. So it should be in the secondary phase, ready to go. And it'll just stay linear all the way up to however many hours that turbine's life was. Some of our turbines were only left for 250 hours on our aircraft. But certainly, secondary phase of creep is the normal, general stretch of the blade, the normal lifetime that it's in the engine. After that, tertiary, we don't want that, so the turbine blade will be removed. Even if it's not broken, it will be removed and the blade's replaced. Okay, good. All right. Well, how do we fit the turbine blades to a disc? What was the type of fitting?
Factory.
Fir-tree, yeah, fir-tree route, yeah, good. And what do we call the type of steel? What range does it come from for the hot environment? The high resistant alloy steel was a certain name we call it. Mnemonic range, yeah. You will get mnemonic locking wire, I've mentioned before, to lock, tighten bolts within the hot system as well. So mnemonic range, very high temperature resistant. Okay. Why is it important to ensure correct compressor and turbine matching?
To obtain maximum efficiency and performance.
Yeah, so what would happen if the nozzle guide vanes restricted the flow? If it
will cause shorts.
Yeah, that's right.
It's compressor to shorts.
Yeah, because of back pressure, it's not going fast enough outside towards the turbine, so you get back pressure, a potential surge with flames and blades going everywhere. Not very good. Likewise, if it allows too much flow, what could potentially happen?
Shock to compressor.
Yeah, shock the compressor. Shock the compressor. Good. Okay. Now we've got no turbines 100% efficient because due to certain things. What could affect efficiency of a turbine?
Like 3-stage will loss in 3.5%.
Yeah, aerodynamic losses, the blades, yeah. I mean, these are just example figures. Don't worry about remember the numbers, but yeah, they're just example figures, but yeah.
Yeah, and the NGVs.
The NGVs as well, yeah. So aerodynamic losses to NGVs and turbine blades, and then the other one is gas leakage over them, just actually escaping through the actual shape and through the exhaust system losses. What we mean by exhaust system losses are things like friction. As the air goes past, it sticks to the exhaust. Okay, and we'll look at that. So the example I've got there, 3.5%, 4.5%, which gives 8% off, which gives us a 92% overall efficiency. Okay. Feed turbines, power turbines. Where would we tend to find those turbine systems? What type of aircraft would you think maybe find those fitted to?
The power turbine.
Yeah, power turbine, also known as a feed turbine. What type of aircraft?
Power turbine will be in helicopters or propeller.
Helicopter propeller, yeah. We'll look at them, we call them shaft drives as well. But again, what's the difference between a feed turbine and a fixed turbine?
Excuse me?
What's the difference between a free turbine and a fixed turbine?
In free turbine, it's not mechanically connected.
It's only the gas that's good.
Yeah.
Good. Okay. Again, if you had the new books there, you might have it in the old books. What I meant to mention as well, if you want to make more torque, okay, if you want to, especially in single stage one, if you want to increase more power, more torque to an engine, that turbine, you could increase its temperature, okay, inlet temperature. By increasing inlet temperature, provided the blades can cope with it, you'll increase power. Okay. Another one is if you increase the diameter of the turbine, well, you've got a bigger rotor, so that can increase more power. And also by increasing the speed, the RPM. So that's 3 ways. If you want to make a note of that, this would be on page 76 of your new books, once you get your new books. I don't know if I'm on the screen there, I apologise there. 3 different ways of producing more torque. So increased inlet temperature, increased diameter, and increased RPM. I'm going to make a note of that somewhere. Only problem with that is if you increase the diameter of a turbine, you increase the weight. So it's a bit of a trade-off, a balance. Do we want to make a bigger turbine? If that makes a bigger turbine, well, we need to make a bigger engine. Can the aircraft cope with the size and space and that sort of thing? We could also increase more stages. More stages, again, that makes more weight. The other thing comes to as well is heat. Can the turbine blades, are the materials suitable? But again, as we go into the future, they're coming up with better materials to produce, take on the stresses there. Good. What was the abbreviation ITT? What did that stand for?
Interstage turbine temperature.
Yeah. And what was TIT?
Turbine inlet temperature.
Good.
And TOT.
Yeah. You could have that one as well. It was turbine outlet temperature. Good.
Outlet temperature.
Yeah. What does NGV stand for?
Nozzle.
Nozzle guide vane.
Nozzle guide. And what shape do they form? Is it convergent or divergent?
Is convergent duct.
Convergent, yeah. You want to speed the gas out of the combustion chamber, so by making it convergent, velocity increases, pressure and temperature decrease. So you'll see a rapid decrease in the temperature and pressure, but certainly we've got the velocity. As the velocity of the air comes out the NGVs, it hits the turbine, and we will lose a bit of pressure and energy, but then the next set of NGVs will speed that gas back up again to help the second stage of the NGVs. Now, what shape was an impulse turbine blade?
Laughing.
Happy smiley faces.
It's smiley face.
Yeah, just
smiley
as you
face.
pass the exam. Yeah.
Cup
And
shape cup.
Yeah, and yeah, like a sort of cup shape. And what shape was an impulse reaction?
Yeah, impulse was cup shape, I think.
Cup shape with a. Looks like a tick. Yeah, it looks like a big tick. Like a Nike tick. You never know Nike, like the trainers. Yeah, so like a Nike tick, or Usain Bolt. You know when Usain Bolt does that? Nike tick.
It's tilted banana.
Whichever way you want to remember. Yeah, happy smiley face for impulse, or impulse reaction is Usain Bolt or Nike for a tick. Good. Okay. When is combustion efficiency 100%?
At sea level.
Condition.
Sea level condition. Yeah, that's when we've got the most dense air at sea level condition. Good. What is the nasty stuff that is produced by the emissions?
Carbon.
Yeah, carbon dioxide. We don't want that. Yeah, carbon and lots of nasty stuff. Carbon dioxide, smoke, and hydrocarbons. Yeah, all really good for the atmosphere. That's not very much at all. Okay, what are the 4 types of combustion systems?
That is reverse flow.
Yeah, that's one.
Annular, annular.
Yeah.
And the multi-chamber, multi-camera.
Yeah, multi-chamber, multi-can. Means that's good. Good. Oh, happy days. Okay, What is the standard air-fuel ratio?
That is 15:1.
And is it by weight or volume?
By weight.
By
Always by weight, yeah. However, that ratio can change over the whole RPM by as much as
45:1 or
1.
130.
130 to 1. Good. And how much of the cooling air, what's the total cooling air percentage in the combustion can?
80%.
20 and
Yeah, 80% for cooling, yeah. 20% for combustion. That 20% gets split into another 2 percentages. What's the other 2 percentages? For the combustion. So 80% for cooling air, we've got 20% for combustion, and that 20% gets split again into 2 more percentages. What were they?
12 and 8.
dilution and
Yeah, 12 and 8, yeah. Which one of the 12 and 8 goes through the swirl chambers?
is 12.
Yeah, 12% through the middle. The swirl chambers, which is like veins, spins the air as it goes through. That helps combustion, yeah. Good. Okay, doke. What are the three flows of cooling air known as?
Primary, secondary, and tertiary.
Good. What does the primary one do?
Mix the
Mix
fuel
with and supports combustion.
support the combustion.
Yeah, secondary.
Second is shape the flame and
Supports-
complete the
Yeah,
combustion.
shapes of flame. Just think shapes of flame. Good. And tertiary.
Cut
Parts
off
Yeah, just cuts the flame off. A pair of scissors in there, cuts the flame off. Yeah. Okay, good. Again, materials in there through mnemonic range. Again, we've seen that already, so it's all good. Happy there. Yeah, that's fine. Okay, that's fine, guys. We shall go for another break, and then we'll start looking at the rest of the subject after tea break. So come back again about 20 minutes or so, 25 minutes, and then we'll do a bit more recap, and then we'll start on the new part after there as well, which I think, where are we now? Get my book. Yeah, exhaust systems are next, yeah. Okay, so we're almost covered the whole engine. Okay, easy peasy. Just left of book 1. Okay, so we'll get there.
I had a nice coffee, sir.
Say again?
What you had, sir? Coffee, tea, something
Oh,
else?
just tea. Nothing exciting, just a cup of tea. Just a cup of tea.
Oh,
Sorting some emails out there as well. Just we'll get a chance. Let's all go here. How about yourself? Do you, anything nice? Have any tea yourself? Any food? Or are you saving that for later? Oh, good. Right.
later.
Say again?
Later,
Right,
sir.
well, yeah. Well, there's not much left. What I'll try and do today is we'll finish book 1 today, and we'll do a little recap today. I think it's my questions on the screen before we start book 2. We'll maybe start a little bit of book 2, but won't go too much ahead because you don't have new books yet, unfortunately. Old book 1 and old book 2, which is the books you've got at the moment, is almost the same-ish as new book 1, if that makes sense. So it will be roughly the same, thereabouts. There's a few bits been taken out, a few bits been put in. So the exhaust system, it's pretty much the same as we had before. There's not much change there. So it should be okay if you find that in the books you've got at the moment. Okay. And then, yeah, we'll do a little recap this afternoon. And we'll try and, we might do a little bit of book 2, but we've got plenty of time for book 2. And by Friday, we'll probably start book 3-ish on Friday. That doesn't take long. It's not a big book. And then book 4 is the last big one. So book 1 and 2, the biggest book. Book 3 is not very big. And book 4 is a bit more in depth. Okay, and we'll try and leave as much of Friday as possible for revision, where we can, as I'm sure we'll have plenty of time. Okay, let's move on to the exhaust system then. So we've done the compressor, we've done combustion, we've done the burners. We're now going to see what happens with the exhaust side of things. Okay, so re-exhaust, to direct the gas flow out towards back, and actually use it to help propel us. Now the temperature, we've seen the combustion chamber can be up to about 2,000 degrees. As it goes back to about the turbine, you're looking at temperature maybe 1,500, and by the time it gets to the exhaust, it's dropped dramatically, because remember, the velocity of the gas has increased, so pressure and temperature obviously decreases. And we can see that there, that roughly 550, maybe 850 degrees or so is the temperature of the gas coming at the back end there. Again, it all depends on the type of engine. But again, still quite hot. It'll still burn you, so don't go near it. Okay. The turboprops and bypass engines of the coolest flows, because the high bypass, remember, you've got bypasses of 5-to-1, maybe even up to 10-to-1, some of the big engines nowadays, big Trent engines. And the turboprop, well, you've got the big mass airflow that's getting pushed back over the engine and then coming back in with it covers it like a blanket over the back of the exhaust, so it helps cool that exhaust gas down as well. That pure jet engine, very hot. Low bypass engines as well, they're still quite hot in exhaust gases. So the use of afterburning, we'll mention afterburning and reheat. Again, we have to mention that because they're still on about bringing Concorde back in. There are other companies making supersonic jets, potentially for commercial aircraft. So we will cover reheat, or afterburners as Americans call it. Again, we can restore engine exhaust temperatures back up to about almost 2,000 degrees, about roughly about 1,700 degrees again. So again, can be quite hot. But again, we'll cover that later on. The exhaust gas flow itself, the gas flow from the turbine enters the exhaust system, and you're looking at about 750, maybe 1,200 feet per second. Okay, so quite fast indeed, quite fast indeed. All right. Now, to reduce the effect of friction losses, and what I mean by friction losses is as the gas is coming down the tube of the exhaust here, it's obviously touching the side of the tube. Well, that's causing friction. Remember, air, go back to module 8, when air goes over the wing at the surface, the friction increases. Yeah. So as the friction increases, so does the air. It gets stickier. Yeah, it gets a lot stickier. So it's going to try and hold that air back a bit more. Again, so the viscosity. Let me go back to viscosity. Viscosity of a fluid decreases with heat, but remember, gas or air does the opposite. Viscosity increases. So you've got that hot gas coming out, so it's already very hot. As it touches the cooler surface of the tube of the exhaust, it becomes stickier, so it tries to hold back a bit. So we'd get a bit of losses. So rather than coming too far, although it's a bit of back to frontness, we want the exhaust gas to come out fast. So when it goes to the propelling nozzle, the back of the exhaust, it pushes the engine forward. But what we do is we slow it down initially to stabilize it. And if you look in the back of the exhaust here, there's your turbine, which would be which one? What turbine would that be if that's the back of the engine?
High pressure.
No, no, no. If that's the back of the engine,
Yeah.
which one will it be? It'll be high pressure, intermediate pressure, or low pressure.
Low pressure.
Yeah, it's always going to be low pressure. If you were stood here looking, yeah, if you were stood here looking into the exhaust and you shine a torch up, you saw the rotating turbine, it's always going to be the low pressure turbine. Yeah. Now, in the back of that, we've got an exhaust cone. Okay, an exhaust cone. Now it's pointy as it comes to the back. So that makes, you can just see here in this diagram, it makes a divergent shape. So between the casing of the exhaust and the shape of the cone, it makes a divergent shape. So that's going to slow the gas down, increase the pressure a little bit, and marginally temperature. So it helps stabilize the gas flow. So it's not going too fast along the skin of the exhaust itself. Okay. We've also got support struts to support the exhaust. And the cone also protects the back of the turbine disc, because the turbine disc in the middle is going a lot slower than the blades on the outside. The tips are going faster than the outside. So you can imagine the air coming out of the turbine is spinning as it's coming from the back. So as it's rotating out the way, it's rotating through, corkscrewing through the air, which is causing friction in the exhaust tube, and we want to straighten that gas flow out. So the supports can act as guide vanes, okay, as well as supporting the exhaust cone, as well. It makes that easier. Now, you can also see here in this diagram, there's a hole in the tip of the exhaust cone just there. Any ideas why that might be? Why not just have a solid cone? Why do you think you've got a hole in the cone that goes all the way through to an empty cavity? Any ideas on that one? What do you think? Why would we have a hole in the cone? Why not just have it to a nice pointy tip? Let's see if you can think of this one.
Sir, where is the afterburner then? In this
Don't worry about that. We'll come on to afterburner.
Where to fit? Afterburner.
What do you think the hole in the back of this exhaust cone is going to be for?
For diffusion, sir.
Yeah, the pressure, yeah. If you've got the fast moving air coming out of the turbine, which goes over, I'm pointing to the screen here, you can't see me pointing, over the cone, but if you've got fast moving air, you've got low pressure. Well, if you've got low pressure on the outside, inside the slow moving air, inside the cone, it's going to be high pressure. So the high pressure is going to win. It's going to try and expand the cone. So by having a hole in the tip here, that equalizes the pressure outside the cone and equalizes the pressure inside the cone. Okay, so it doesn't expand out. So we get a divergent shape, slows it down initially, then the gas will stabilize, it'll come down towards the end of the exhaust. And as you can see here, we've got the propelling nozzle at the end of the exhaust, which is convergent in shape. So at the end, it converges, speeds up the gas, and that propels the gas out the back end, which propels the engine forward. Newton's third law, every action is equal and opposite reactions. The gas comes out, pushes the engine forward, and the engine is attached to the aircraft, it pushes your aircraft forward. So that's the basic insight there. The gas flow, now we've got a couple of bits going on here. Looking at side flow, somebody's got a microphone on. Here we've got, if you look here, we've got just an example. It's a three-stage, well, it could be a twin spool engine. We've got maybe a two-stage LP turbine and maybe a single-stage HP turbine. Okay, now there's the exhaust cone again. And as you can see, we've got divergent shape going on, so it stabilizes it. But the exhaust section here is also convergent, okay, which will propel it out. Now, this one happens to have a divergent exhaust attached to it. That would be like a rocket, you know, or we don't tend to have these on commercial aircraft. That would be for supersonic engines as well, but we don't have that commercial use. Just give an example of what's going on. That would be what's called a con-die nozzle, but don't worry too much about that, just for a bit of background information. Choke nozzle, this is your standard one, okay? So this is what's going to happen in a standard exhaust type system. So there's your turbines, okay, the two-spool engine, the fusing section, so it stabilizes the gas coming out. As it gets towards the propelling nozzle, it's going to do a few things. So that diameter there is crucial. If it's too big, we won't get enough back pressure. We need back pressure in the system for the engine to grab all that pressure, all that air, and go, right, I am ready to give that exhaust gas out. The engine, the compressor's working correctly, and the turbine's working correctly, everything's working right. If we have too big a hole, that's like putting, I'll go back to the cars again, you probably see some people put massive exhausts on the cars, right? What does that do to the car? It makes it sound very, very loud. What does it do to power? Nothing. Okay, does anybody have a car or motorbike with a very big exhaust on it? Yeah, sounds great, doesn't it? Nice and loud. It actually reduces the power of your engine. Sounds great. Yeah, you get big sort of noisy, raspy sound. Fantastic. So you're one of the boy racers, as we call it. Unless you put a bigger air filter in and put more fuel in, you won't get any more power. You actually reduce the back pressure in your engine, and you're actually losing maybe 5-10 horsepower of your engine. Okay, it sounds great though. It sounds very sporty. All right. But for jet engines, very crucial. Some of you probably have motorbikes, 4-stroke motorbike, not so bad, but certainly a 2-stroke motorbike. If you've got a 2-stroke motorbike, the expansion chamber is quite large. My son used to have a little DT125, and it's got a quite, as the exhaust comes out, it goes a big expansion chamber, then goes to a smaller silencer. Well, that expansion chamber is divergent in shape than convergent. If you used to cut it off, it'd be very noisy, you'd have no back pressure and the engine would lose power. Okay, so it's crucial that the diameter of the exhaust matches the power output of the engine. If that's too small, that'll cause a lot of back pressure. A lot of back pressure through the turbine, it's going to cause potential surge. Too big a diameter, it's going to breathe too easily. Well, then you can possibly, like we saw before, like NGVs, we could stall the compressor. Yes, you'll get gas coming out, but no direction and no official proper thrust. So it's quite crucial. So the right diameter will give us what's called a choked nozzle condition. And that's a good thing, providing it's the right diameter. When we say it's choked, that's when the airflow, as it comes out the turbine, has become sonic and the speed of sound. Not supersonic, not subsonic, it will be subsonic to start with, but when it comes sonic, that is in what's called a choked position. That's when the engine is happy. It's got, right, I've got the right pressure, I've got the right back pressure, I've got the right pressure NGVs, the turbines, the compressor, it's all good. We're in a choked position. If it gets more than that, then there's either too much fuel going in and we're going to overstress the engine. Not enough choke position, we won't get the right thrust. Okay, so a choke position is actually, in this case, good. So that's when the pressure builds up. Okay. Same pressure will start, you actually get pressure going back the way. Okay, now providing it's the right diameter, that is okay, that is fine. It's when it exceeds that amount of pressure, that's when things go wrong. Then we get what's called pressure thrust. When the choke nozzle becomes choked, we get the right amount of pressure in the exhaust system. That will propel the gas out into what is called pressure thrust. Okay. That's when we get choke nozzle, speed of sound, sonic condition, oxygen pressure is good. We get our pressure thrust. Okay. Construction materials, so that would be us looking up the exhaust. Okay, there's a looking from the back. You can just see the turbine in the back here. But this exhaust system, this has actually got reheat in it. These little extra bits, we'll cover reheat in a little while, don't worry about it. But there's the exhaust cone. Okay, don't worry about these manifolds at the moment. That would be, this is a military aircraft. As you can see the blades of the turbine, which would be obviously the LP turbine. Okay. So construction materials, got various types. They've got to be obviously withstand temperatures and pressures. Okay, so again, mnemonic range. And again, here's another high bypass engine. You can see the compressor at the front. There's the exhaust cone. There's the LP turbine. There's the support struts. Okay, going round, all the way around. Again, high bypass engine. Give you a size, an indication of size. You can see the man there. Okay, so he's got the cowling doors open to inspect the engine. So quite a large engine there itself. And again, if you were to spin that turbine, you'll spin the LP spool. You won't spin the internal engine because the LP spool is separate. So that's the LP turbine. Okay. Now, depending on design, again, we can use the cowlings to actually help mix the gas at the back. Okay. Now, some engines don't have any cowlings. Is what the doors that cover the framework that covers an engine. Okay, so in this one, there's none at the back, it's quite open. But in this one, it does. It's got what's called a common or integrated nozzle assembly. That can help propel as well. It all depends, again, on the type of engine. Now, what I was going to add in there before we're going to thrust reverse is, that one's all right. No, we've covered that one, that's okay. I'll just make sure on the new book, there's nothing else there. Yeah, that's all right. It should be pretty much the same as in your old books. There's nothing I can see that's changed too much from your old books. Okay. Only bit with the pressure thrust, just to recap that one. As I said there, when the nozzle becomes choked, it becomes sonic. The speed of the gas has become sonic, as in the speed of sound. The exhaust gas can't go any faster, so it starts to go back away, which causes an upstream pressure, which is what we want. Okay, pressure difference will cause exhaust gas to escape through the nozzle and then naturally equalise once it gets to the atmospheric pressure. Okay, and that's what we call pressure thrust. Okay, so it's important that if we find any damage on the nozzle, that could potentially cause problems with the pressure thrust. You know, so again, if maybe somebody's hit it with a vehicle or something, potentially damage, or it's been a heavy landing, whatever, again, we don't want any problems there. Some exhausts, they might have insulating blankets as well, because obviously we've got a lot of heat coming out. You can see the bypass here, the high bypass here coming around and covers the hot gas coming out. Now that does a few things. That also helps cool the exhaust system, and this cold air, which will come on to noise reduction in a little while, also helps blanket the hot air. Now hot air going through atmospheric air is very turbulent, very what I call raspy, and it can make a lot of noise. If we cover it with cold air, that helps muffle the noise. So again, we'll come on to that in noise insulation. Blankets, you can use fibrous layers. Again, helps heat insulation, it'll help noise and that sort of thing. We can also have ejectors that actually induce the atmospheric air from outside, because you've got the fast moving air inside, which induces the slow moving air from outside, and that can help draw it in as well. The mixer unit, okay, this can be called a mixer unit as well, which mixes the cold air with the hot air. Again, but there's lots of different designs as such. So, I mean, again, it all depends on the type of aircraft and engine you're working on. Okay. Right, so we're not far off. We've got thrust reverse next. We'll leave that for after the lunch, I think. We'll thrust reverse and noise reduction after lunch. Yeah. Okay, we've got about 10-15 minutes for lunchtime. What we'll do is recap again, make sure we're happy with some of the terminologies, and we'll start with thrust reverse and noise reduction, and a few more questions after the lunch. So, to save going any further. So I'll leave that there for a moment. So that'll be where we'll start after lunch. Okay, so quickly recap what we just mentioned there. If I said the exhaust gas flow is in a choke condition, what has happened there? What's happened when the exhaust gas flow is in a choked condition?
Is a sonic.
Yeah, it can't go any further. The gas flow has literally choked itself, but because of the design of the exhaust, that's good. If it's too small, it's not good. If it's too big, again, not good. The design of the exhaust is for that power of the engine. So it becomes choked. So eventually it's going to try and push itself out the exhaust, and it'll speed up. So that'll give us our thrust, which is called what type of thrust?
Pressure thrust.
Pressure thrust, good, yeah. So nozzle choke condition, no further increase in velocity. In other words, it's going as fast as it can. The upstream pressure will increase, and eventually it will bang out the nozzle, and that'll give you your pressure thrust. Good. Okay. What's the sort of temperatures you might find in the exhaust system itself? Yeah, and although we're not covering it, we mentioned reheat. It can go up to roughly, if we add reheat or afterburner on there. Yeah, good. Okay. What is the speed of the gas roughly as it enters the exhaust from the turbine?
Per second. 750 to 1200.
Yeah, 750 to 1200 thereabouts. Good. Again, temperatures definitely remember. Speeds, I've not seen many questions. It's good to remember just in case, because if we don't get to see the questions, we might have to change questions. Okay, going back away for materials of turbine blades. What were the three types of materials from the early ones up to the modern ones? What were the three types of materials used in turbine blades? What have we got there? Anybody remember 3 names?
The crystal, you mean crystal plate?
Yeah, single crystal, that's the most modern one.
Yes, single crystal and directionally solidified structure.
Yeah, that's the in-between one. That's the not as old but not as new yet. What was the really old one?
Old one is the skewed crystal structure.
Yeah, equiax crystal structure. Good, 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 good. Again, the equiax ones, they were good, but they had all the grains. Grains are boundaries. The boundaries are weak points, so they were prone to not lasting as long as a single crystal. Okay, so good there. So what is blade creep? What is turbine blade creep?
In dynamic.
What do you mean by blade creep? Everybody?
One second, question, please.
So blade creep, what does that mean? Reference to a turbine blade. The clue? That's another name for stretching of the blade, isn't it? Yeah.
The stress due to the aerodynamic and centrifugal or thermal.
It's more, just think of the blade stretching, the centrifugal force, yeah? It's going to bed in, eventually because of the centrifugal force, it's going to stretch the blade. So we call it stretching, we call it blade creep. It's creeping away, yeah? It's getting further and further away. So remember, we've got primary, secondary, and tertiary, okay? So primary is initial bedding in, secondary is the normal working life of the turbine blade. So however many hours that gets allocated to the engine. But we don't want to use the engine when the hours gets into the tertiary area. That's when there's a good chance the blade's going to fail. So the normal working life of a turbine blade is usually in the secondary time scale of the blade creep. Okay. Okay. What was the type of turbine blade fitting to a disc?
Is fair tree root.
Fairtree root, yeah. And the type of steel that gets used, what was the name of the range? So the high, yeah,
Mnemonic
good. Yeah, mnemonic steels. Good, good, good. And the good one is the compressor turbine matching. What would happen if the NGVs provided too much flow?
Too much flow is compressor choke.
Yeah, compressor choke, yeah. And too low a flow?
Is surge.
Surge, good. Good, good, good. So in other words, it's going to affect the efficiency. All right. Power turbines, feed turbines. Again, we're using what type of aircraft?
Is a helicopter or propeller aircraft.
Yeah, good. Okay, and the one that's in my book, not in the PowerPoint, was how can we increase the power depending on materials or provide more torque? There was 3 things.
Is temperature increase, diameter enlarge, and RPM increase.
Yeah, good. Yeah, temperature, diameter, and RPM. Again, there's pros and cons of all those ones, like weight induced. RPM, well, more RPM, that can put more stress on the turbine blades, so that can induce more creep. So that could reduce the hours of the secondary stage of the turbine creep because we're putting more centrifugal force on. So yeah, it all depends on materials being used. As long as they can cope with that, then greater. The hotter we can get the inlet temperature, the more efficient a turbine itself can become. Good, 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 good. Okay, good ones. What was the names for the shapes or the profiles of the turbine blades?
One is cup shape and another is big neck tick.
Big Nike tick, yeah. Yeah, it's basically a cup shape followed by a profile. Okay, so it looks like a Nike tick or a happy smiley face for impulse. So impulse and impulse reaction, the official ones. But as long as you remember which one they are, whichever name you want to put to it, it'll help you for the exams, which is always a good thing. When is combustion efficiency 100%?
No.
When is it combustion efficiency at 100%? Sea
Sea
level.
level.
Sea level, yeah.
Sea level, good. Right, can anybody remember the names of the cooling air liners? There's the 4 types of names. So on the cooling liners of the combustion cans, there's different shapes.
So that is machined cooling ring,
Yeah, machined, yeah.
splash cooling strip,
Splash, yeah.
and transpiration cooling,
Yeah, transpiration.
and corrugated spring cooling.
Good, corrugated, good. What were the 4 types of combustion chambers?
Can type, annular type, reverse type,
Yeah.
and can annular.
Good, 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 good. Okay, if I said to you that 12% of the combustion air goes through what? What does the 12% air flow through?
12% will go directly to combustion chamber through the fuel.
Through the swirl veins, that's the main one, yeah, through the swirl veins. Good, 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 good. Now you've got inner zone and outer zone, I'll say inner layer, outer layer. What was the total percentage of cooling air? Percentage of cooling air.
Excuse me, for what?
The total percentage of cooling air.
80% is for the cooling purpose.
Yeah. And that's split into 3 parts, which were? What was the names of the 3 parts?
Primary zone and dilution. Dilution zone.
Yeah, there's primary zone, dilution, and then we split that down to 3 parts, which was? What was the names?
And dilution for 40 and 20.
Yeah, so what was the names we called? There's primary dilution. Dilution is also called tertiary. So we've got primary, secondary, and tertiary. What did primary do?
Mixing with fuel. And
Yeah, support combustion. Secondary?
Complete combustion, right?
Yeah, shape the flame.
Yes,
Complete
with
combustion.
shape,
And
yeah.
tertiary?
Cut off the flame and reduce gas temperature.
Yeah, good. Just cuts the flame. What it does, it stops the tip of the flame touching the NGB, potentially burning away. Good. All right, the fuel-air ratios. What was the standard fuel-air ratio?
15 is to 1.
Yeah, 50 parts air to 1 part fuel. And what could it potentially be over the entire RPM range?
45 is to 1 and 130 is to 1.
Yeah, good. And it's always by weight. Yeah, always by weight. Good.
Weight.
So, yeah, what's the approximate temperature that would be found in a combustion can?
2000 degrees Celsius.
Yeah, good. Very, very hot. Right. Okay, give me an example of an atomizer burner. So there's quite a few types. So give me an example of an atomizer burner.
Simplex burner, duplex,
Yeah,
spray nozzle,
yeah,
and air spray nozzle.
yeah. There's another one that goes round.
Another one, air.
You might not have it in your old books. I think it's in the new book only. The rotary one. The rotary one.
Rotary.
Okay. So we've got atomizer burners. What was the other type of burner?
Vaporizing.
Vaporizing, yeah. And what was a name given to the vaporizer? What was a common name? Because it looked like something.
Hockey stick.
Yeah, hockey stick. And what was special about the vaporizer burner compared to an atomizer?
is tend to facing forward.
Yeah, and what about the fuel entering the vaporizer? What happens to it before it goes to the vaporizer? Yeah, preheats it. Yeah, we preheat the fuel so it comes like a steam and such. Okay. Good. All right. What is the purpose of a pressurizing valve?
To increase pressure.
Yeah.
High enough.
You're not wrong. You're not wrong.
Yeah.
Yeah. What does it ensure? What does it ensure?
It's high enough pressure in the primary fuel flow.
Yeah. What is another name for this pressurizing valve? What's it also known as?
Back pressure valve.
Pressure valve. Yeah, good. So you might also incorporate a distributor weight valve, but it just ensures that under all conditions that the fuel pressure is up to speed. Okay. It's fitted when there's sometimes two fuel flows, but against main flow to ensure there's enough pressure in the primary flow to provide atomization at low fuel pressures. Okay, good. Yeah, okay. Out of the two flows, primary and main flow, which one is always available when you open high pressure cook? Primary or main?
Primary fuel flow.
Yeah, it's always available. It's not as much as the main one because we don't want all the fuel to start with when we start an engine. Okay, so primary, as soon as he opens the HP cock, that fuel flow is available. There's no distributor weights. Okay, pressurizing valves will ensure the pressure is okay, but it doesn't need distributor weights, and that is all good. Otherwise, if we put too much fuel in straight away, we can get hot spots and over fuel the engine, and which we don't want either. Good. And that takes us up to food time. Right? So you can go and get some food. Right. Okay, guys. Any questions before we head off for my lunch and your tea?